All right, welcome back to the deep dive.
Yeah.
Today we're going deep, really deep, into the world of gold extraction.
Yeah, we're going for gold today.
You've given us a real treasure trove of information to sift through um, course notes, evaluations, research papers, covering every step of how we get gold, from rock to riches, so to speak.
Yeah, and we're not just talking about the technical stuff. We've also got some really interesting insights into the environmental side of gold mining. How do we
Yeah.
minimize the impact, right?
Right, absolutely. So our mission today, well, we're going to follow that journey of gold, from the moment it's just a glint in a rock all the way to those shiny bars we see in vaults and on TV.
And along the way, we'll be taking a hard look at the environmental challenges and how the industry's tackling those. It's a big topic, but let's dive in.
Okay, let's get started then. So you can't just walk around and pick up gold nuggets off the ground,
Not usually.
sadly. It all starts with understanding what we're dealing with, the ore itself.
Yeah, exactly. The gold extraction short course really emphasizes that point. The first step is knowing your enemy, right? Or in this case, knowing your ore.
And knowing your enemy means knowing, well, what kind of gold is in there? Like what specific minerals hold the gold and what else is mixed in with it. We're talking about sulfides and something called gangue.
Right. Gangue minerals, that's the stuff you don't want. It's basically the rocky matrix that the valuable minerals are trapped in.
So it's kind of like a cosmic game of hide and seek,
Yeah.
right? Find the gold hidden and all that other stuff.
Exactly. Now, traditionally, the way you'd find visible gold was literally with a microscope. A skilled operator would look at a polished section of the ore and try to spot those little flecks of gold.
But that seems, well, kind of subjective, right? And slow. I mean, some gold minerals, as the notes say, can be pretty tricky to identify. Like, they're not always that classic shiny yellow color.
Yeah, you're right. Some gold minerals can look almost white or grayish. And then there's the issue of misidentifying other minerals that might look similar under the microscope. It can be a real challenge.
So it's not just a matter of, ooh, shiny, that's gold.
No, definitely not. And that's why, as technology advanced, things really started to change. Enter the electron microprobe, the EM. It's like the high-tech detective of the mineral world.
Okay, so EM, that's like a super microscope, right?
It is. It uses a beam of electrons to interact with the sample. And what's really cool is that it's often linked to an image analyzer. So the system can actually scan those images from the EM and automatically pinpoint the bright spots, the ones that could potentially be gold.
Oh, so it's like having a robot prospector.
In a way, yeah. And the best part, it can even detect what we call invisible gold. That's gold that's so finely dispersed or locked inside other minerals that you can't even see it with a regular microscope.
Okay, so now we're talking about like microscopic, even smaller than microscopic gold.
Exactly. And this is where things get really interesting because a lot of gold ores, especially the ones being mined today, have very low concentrations of gold. We're talking parts per million. So finding those tiny specks is crucial.
Wow, so it's like looking for a needle in a giant haystack, except the needle is microscopic.
Pretty much. And that's why the source material talks about the importance of preparing multiple polished sections of the ore for analysis. Like you might need 4, 5, even 6 sections just to get a statistically representative sample.
So it's not just one quick peek under the microscope, it's a whole process, right?
Yeah, it is. And if the ore grade is really low, then you might even need to use concentration techniques. These are essentially ways of separating the heavier minerals, including the gold, from the lighter gangue minerals.
Ah, so it's like panning for gold, but in a super high-tech lab.
That's a good analogy. You're using things like heavy liquids or special centrifuges to separate the gold based on its density.
Clever. Now, the notes actually give us some really specific examples of how gold occurs in different ores. They talk about the Gruesa and Bruja veins, I think it was.
Oh, yeah, those were fascinating. What was really interesting there was how the gold was distributed within the ore. In those veins, they found that about 80% of the gold was associated with sulfide minerals, mainly galena and arsenopyrite.
So like little particles of gold kind of stuck to or embedded in those sulfides?
Exactly. And the remaining 20% was linked to silicates, which are another type of mineral.
And this distribution information is really important, right? It's not just about finding the gold. It's about understanding how to get it out.
Absolutely. Knowing how the gold is associated with other minerals tells you a lot about how you might need to process the ore to liberate that gold and recover it efficiently.
And then there's the whole mystery of invisible gold, which we touched on earlier.
Ah, yes. The gold that's hidden from view. It might be present as tiny inclusions within other minerals, or even dissolved within the crystal structure of those minerals.
So how do you even begin to analyze something that you can't see?
Well, that's where techniques like secondary ion mass spectrometry or SIMS come in. SIMS is incredibly powerful. It can analyze the composition of individual mineral grains at an incredibly fine scale.
Wow, so it's like a chemical fingerprint for each tiny grain.
That's a good way to put it. And by analyzing those fingerprints, researchers can pinpoint the presence of gold, even if it's only present in trace amounts.
It's like having a super sleuth on the case, right?
Yes.
Uncovering the hidden gold.
Exactly. And the notes give us some really cool real-world examples of this, like the analysis of the Trout Lake tailings.
Oh yeah, the tailings. That's the leftover material after the initial processing, right?
Yeah, basically the waste rock. But even in those tailings, they found a significant amount of invisible gold. Like 27% of the remaining gold was trapped inside pyrite, another 9% was in arsen pyrite, and get this, a whopping 64% was actually visible gold, but in such tiny inclusions within pyrite that it wasn't recoverable by conventional methods.
So even the waste isn't really waste. There's still gold hiding in there.
Exactly. It highlights the need for more advanced and targeted extraction techniques.
And they also looked at a composite sample from the Pasqua mine, right?
They did. And that one was interesting because the visible gold there was mostly in the form of native gold, the pure metallic form, and also some gold tellurides.
So each deposit has its own unique fingerprint, its own way that the gold is distributed and locked up.
Absolutely. And that's why mineralogical analysis is so crucial. It's like doing detective work at the atomic level.
Okay, so we've found the gold. At least we know where it is. Now how do we actually get it out?
Well, one of the first steps in that process is often gravity recovery.
Okay, gravity recovery. That sounds pretty straightforward.
Right.
Like just letting the gold settle to the bottom.
Well, it's a bit more involved than that. The basic idea is to use gravity to separate the heavier gold particles from the lighter gangue minerals. But the efficiency of that separation depends on a lot of factors.
Like what?
Well, for starters, how well the gold is liberated from the surrounding rock. If the gold particles are still locked inside those other minerals, gravity alone won't do much.
Ah, that makes sense. So you need to crush and grind the ore to free up the gold first.
Exactly. But there's a catch. If you grind the ore too finely, you can actually reduce the amount of gold that's recoverable by gravity.
Wait, what? How does that work?
Well, think about it. If you grind the gold down to really tiny particles, they might not have enough mass to settle out effectively, even under gravity. They might just get carried away with the lighter minerals.
Huh, so there's like a Goldilocks zone for grinding. Not too coarse, not too fine.
Precisely. And that's where computer simulations come in. They can help predict how much gold will be recoverable by gravity at different grind sizes.
And the notes also talk about something called the circulating load. What's that all about?
Yeah. So in a typical grinding circuit, you have this continuous flow of material. The ore gets crushed, then it goes to the grinding mills, and then it's separated using cyclones, which are basically like high-speed centrifuges.
Okay, so they spin really fast and separate the particles by size.
Exactly. The finer particles go on to the next stage of processing, while the coarser particles are sent back to the grinding mills. And the circulating load is essentially the amount of material that's constantly moving through the cycle.
And why is that important for gravity recovery?
Well, the efficiency of gravity recovery depends not just on how much gold is present, but also on how much of that gold is circulating in that load and how well it's captured each time it passes through the gravity recovery unit.
Oh, so you want the gold particles to have as many chances as possible to get caught by the gravity separator.
Exactly. And that's why the performance of those cyclones is so critical. If a cyclone isn't working properly, it can actually lead to gold losses.
Wait, really? How so?
Well, if the cyclone is malfunctioning, it might send some of the gold particles, the ones that are actually heavy enough to be recovered by gravity, to the wrong stream.
So like sending them to the finer particle stream instead of the coarser one?
Exactly. And those particles might then end up bypassing the gravity recovery stage altogether.
That's a costly mistake.
It can be. That's why it's so important to carefully monitor and control the operation of those cyclones.
And before a mining operation even thinks about setting up a gravity recovery circuit, they need to test for something called GRG, right? Gravity recoverable gold.
Yes, absolutely. GRG testing is crucial. It tells you how much of the gold in the ore is actually amenable to gravity recovery, and that information is essential for designing the right kind of recovery circuit.
And these tests can be pretty simple, right? Like just panning for gold in a lab.
Well, some tests are fairly straightforward. Batch tests, for example, can be done in a relatively simple lab setup, but other tests can be much more complex.
Like what?
Well, sometimes they'll actually run pilot scale tests where they build a mini version of the actual gravity recovery circuit and test it with real ore.
Wow, so it's like a dress rehearsal for the real thing.
Exactly. It helps to iron out any kinks and make sure that the circuit is going to work efficiently.
Now, when it comes to the actual technology used for gravity recovery,
Hmm.
our notes mention a whole smorgasbord of different units. Nelson concentrators, Falcon concentrators, inline pressure jigs, spirals. It's like a gold-catching toolkit.
It is, and each of those units has its own strengths and weaknesses. Some are better suited for coarser particles, others for finer particles. Some are continuous, others are batch. It really depends on the specific characteristics of the ore and the overall design of the processing plant.
So how do you choose the right tool for the job?
Well, that's where the expertise of the metallurgists and the process engineers comes in. They'll look at the GRG test results. They'll consider the flow rate of the material, the particle size distribution, all sorts of factors.
And the notes specifically mention that the feed rate can affect the recovery efficiency in some of these units, like the Nelson concentrator. Why is that?
Well, in a semi-continuous unit like a Nelson, you have these cycles where the heavy minerals, including the gold, are concentrated, and then a flushing cycle to remove that concentrate. And if you feed the material in too quickly, the gold particles might not have enough time to settle out and be captured before the flushing cycle starts.
So it's all about timing, right? Giving
That's
those
all
gold
about.
particles enough time to do their thing.
Exactly. And that's why careful control of the feed rate is so important.
And just like with the mineralogical analysis, we can use mathematical models to predict how these gravity circuits will behave, right?
Yeah, absolutely. These models are incredibly sophisticated. They take into account things like the particle size distribution, the GRG test data, information about the cyclones, and even data from other similar operations.
So they're like virtual versions of the real world circuit.
They are, and by running simulations, the engineers can optimize the design and operation of the circuit to maximize gold recovery.
Now, what happens to the concentrate after it's been recovered by gravity? I know that traditionally they used a process called tabling to further upgrade it, but the notes suggest that there's a new kid on the block.
Yeah, tabling is still used in some cases, but it's definitely becoming less common. The trend now is towards intensive cyanidation of those gravity concentrates.
Intensive cyanidation. So that's using cyanide to leach the gold from the concentrate.
Exactly. But because the concentrate is already, enriched in gold, you can use a much higher concentration of cyanide and often higher temperatures and pressures as well.
And that results in much higher gold recoveries, right?
It does. We're talking 95 to 99% recovery.
Wow, that's impressive. So why isn't tabling used as much anymore?
Well, tabling has a number of limitations. For one thing, it's very labor intensive. You need skilled operators to run those tables, and it's also not as efficient as intensive cyanidation, especially when you're dealing with very fine gold particles.
And the notes also mention some potential safety concerns with tabling.
Yeah, the concentrates produced by tabling can sometimes contain harmful elements like mercury or arsenic, and smelting those concentrates can release those elements into the environment.
So intensive cyanidation is not only more efficient but also safer.
Generally speaking, yes. And the notes describe a couple of different technologies used for intensive cyanidation, the batch inline leach reactor, or ILR, and the Acacia reactor.
And these are specifically designed to handle those high-grade concentrates.
They are. They're designed to achieve very high levels of gold extraction in a relatively short amount of time.
Okay, so we've covered gravity recovery and the treatment of concentrates. Now let's talk about the main event, the cyanidation of the bulk of the ore.
Wow.
This is where the real magic happens, right?
It is. Cyanidation is the heart of gold extraction. It's the
Big time.
process that actually dissolves the gold from the ore and puts it into solution.
And it's been around for quite a while, right?
Oh yeah. The process was patented way back in 1887.
Wow, that's over 130 years ago. So what's the secret sauce of cyanidation? What makes it so effective?
Well, it's the cyanide itself. Cyanide has this unique ability to dissolve gold in the presence of oxygen.
And it's a pretty simple process, right? Just dump some cyanide into the ore and watch the gold disappear.
Well, not quite that simple. There's a lot of chemistry involved. You need to carefully control the pH, the temperature, the concentration of cyanide, all sorts of things.
So it's like a delicate dance between the cyanide and the gold.
Exactly. And the notes actually go into quite a bit of detail about the chemical reactions that are taking place.
Oh, okay. Like what?
Well, for example, they talk about how cyanide reacts with oxygen to form cyanate, which is a less toxic compound. But cyanide also reacts with various sulfur compounds in the ore, forming thiocyanate, which is a major consumer of cyanide.
So you can actually lose cyanide during the process.
You can. And that's why it's important to monitor and control those side reactions.
And cyanide also reacts with other metal ions in the ore. Right?
It does. It can form complexes with metals like copper and iron, and those complexes can actually interfere with the gold dissolution process.
So it's not just about dissolving the golds, it's about managing all these other reactions as well.
Exactly. It's a complex system. And the notes provide a really good overview of the key factors that influence the efficiency of cyanidation.
Like what?
Well, they talk about things like the surface area of the gold particles. Smaller particles dissolve faster.
That makes sense. More surface area, more contact with the cyanide.
Exactly. And they talk about the concentration of cyanide, the concentration of oxygen, the temperature, the pH, the presence of other ions.
Wow, there's a lot to consider.
There is, but luckily we have tools to help us understand and manage all of those factors.
Like what?
Well, mathematical models, for example. We can use models to simulate the cyanidation process and predict how different variables will affect the gold extraction rate.
So we can kind of run virtual experiments before we do the real thing.
In a way, yes, and that helps to optimize the process and make sure that we're getting the most gold out of the ore.
And the notes also mention the importance of cyanide management.
Right. Cyanide is a hazardous chemical, so it's essential to handle it safely and responsibly.
And I imagine it's also important to minimize cyanide consumption, right, for both economic and environmental reasons.
Absolutely. And there are a number of technologies and strategies that can be used to reduce cyanide consumption.
Like what?
Well, one example is the use of online cyanide analyzers. These instruments can continuously monitor the cyanide levels in the leaching circuit and allow for very precise control of the cyanide addition.
So you're not just dumping cyanide in willy-nilly. You're carefully adjusting the levels based on real-time data.
Exactly. And that can lead to significant cost savings.
And the notes also talk about technologies that can improve the mass transfer of oxygen into the leaching slurry, like that fill blast reactor thingy.
The fill blast gas shear reactor, yeah. That's a really cool piece of technology. It's designed to increase the dissolved oxygen levels in the pulp and to improve the contact between the oxygen and the gold particles.
And that helps to speed up the leaching process.
It does. And the notes conclude the cyanidation section with a couple of interesting case studies.
Oh, yeah, the Musselwhite mine and the Fimiston operation, right?
Exactly. The Musselwhite case study showed how increasing the dissolved oxygen levels and adding a bit of lead nitrate to the slurry could significantly improve gold extraction from their particular type of ore.
And what about Fimiston?
Well, they found that they could improve gold extraction from their concentrate by by modifying the leaching conditions, specifically by increasing the concentrations of lime, dissolved oxygen, and cyanide.
So it's all about fine-tuning the process, right? Finding the optimal conditions for each specific ore type.
Exactly. And these case studies are great examples of how those fundamental principles of cyanidation can be applied in real-world situations.
Okay, so we've leached the gold into solution. Now we need to get it back out. And that's where activated carbon comes into play, right?
It does. Activated carbon is the gold catcher, so to speak.
And it's incredibly effective, right? The notes say that over 70% of all the gold mined globally is recovered using activated carbon. That's a huge number.
It is. It's become the industry standard for gold recovery.
So how does it work? What's so special about activated carbon?
Well, activated carbon has this amazing ability to absorb gold from solution. It's like a sponge for gold.
Okay, so the gold basically sticks to the surface of the carbon.
Exactly. And there are a few different ways that activated carbon can be used in gold processing.
Like what?
Well, the three main processes are carbon in pulp, or CIP, carbon in leach, or CIL, and carbon in column, or CIC.
And what's the difference between those?
The main difference is in the timing of when the activated carbon is added to the process.
Okay, so in CIP, the leaching and the adsorption are separate steps.
Right. You first leach the gold from the ore, and then you add the activated carbon to absorb the dissolved gold.
And in CIL?
In CIL, the leaching and the adsorption happen simultaneously. The activated carbon is actually present in the leaching pangs.
And CIC?
CIC is a bit different. In CIC, the pregnant solution, the solution containing the dissolved gold, is passed through a column filled with activated carbon.
So the carbon is kind of like a filter trapping the gold as the solution flows through.
Exactly. And each of those processes has its own advantages and disadvantages.
Like what?
Well, for example, CIP is generally more efficient in terms of gold recovery, but it requires a more complete leaching of the gold upstream.
And CIL?
CIL can be advantageous if the ore leaches quickly, but it typically requires a higher carbon inventory. You need more carbon in the circuit.
And what about CIC?
CIC is often used for smaller operations or for treating solutions that are already pretty high in gold concentration.
So it's like a specialized tool for specific situations.
Exactly. And the notes really emphasize the versatility of these carbon-based processes. They can be used to treat a wide variety of feed materials, from raw ores to concentrates to even old tailings.
And they're pretty robust, right? They can handle variations in ore grade and other operating conditions without losing too much efficiency.
Yeah, they are. And that's a big advantage in a real-world mining environment.
So activated carbon is like the reliable workhorse of gold recovery.
It is. Now, the efficiency of gold absorption onto activated carbon depends on a number of factors.
Like what?
Well, the size of the carbon particles, for one thing. Smaller particles generally have faster absorption rates.
Makes sense. More surface area, more places for the gold to stick.
Right. And the concentration of carbon in the pulp is important, too. The higher the carbon concentration, the more gold you can absorb.
And the mixing, right? You need good mixing to make sure that the gold ions in the solution are coming into contact with the carbon particles.
Absolutely. And the temperature also plays a role. Higher temperatures generally lead to faster absorption.
But that can also increase energy costs, right?
It can. And the chemistry of the solution itself is important too. Things like the pH, the cyanide concentration, the presence of other ions.
It's all connected.
It is. And the properties of the activated carbon itself can also affect adsorption.
Okay, so not all activated carbon is created equal.
Not exactly. Different types of activated carbon have different surface chemistries and different pore structures.
And the notes mention something about the reduction potential of the carbon being important.
Yeah, the reduction potential can influence how strongly the carbon absorbs different gold cyanide complexes.
And what about the pores?
Well, activated carbon has this intricate network of pores, tiny little holes throughout its structure. And the size and the accessibility of those pores can affect how easily the gold can get in and out of the carbon.
So it's not just about the surface of the carbon. It's about the internal structure as well.
It is, and
Yeah.
the kinetics of absorption, how quickly the gold absorbs onto the carbon is often described as a two-step process.
Okay, what are the two steps?
Well, the first step is a rapid absorption onto the external surface of the carbon. That's controlled by diffusion, how quickly the gold ions can reach the carbon surface.
So it's like a mad dash for the open seats.
Exactly. And the second step is a slower diffusion into the internal pores of the carbon.
So once the easy spots are filled, the gold has to work its way into the nooks and crannies.
That's a good way to put it. And plant operations typically aim for a sort of pseudo-equilibrium in the larger pores, the macropores and the mesopores.
Why is that?
Well, because that allows for both fast extraction and an efficient elution later on.
Okay, elution. We'll get to that in a bit. But first, let's talk about carbon distribution in the CIP circuit. The notes say that it's important to have a uniform distribution of carbon in the tanks.
Yeah, it is. You want to make sure that the carbon is well mixed with the pulp so that it has the best chance of contacting those gold ions in the solution.
So no clumps of carbon hanging out in the corner.
Exactly. And the total amount of carbon in the circuit, the carbon inventory, is also an important factor.
Why is that?
Well, you need enough carbon to effectively absorb the gold, but too much carbon can lead to higher operating costs. The carbon itself costs money, and it also takes energy to move it around and to regenerate it.
So it's a balancing act.
It is, and the notes point out an interesting phenomenon that can happen in CIP circuits.
What's that?
Well, they say that some additional gold can actually be recovered in the adsorption section due to desorption of gold cyanide complexes from the ore particles themselves.
Wait, what? So the gold can actually come off the ore and then reabsorb onto the carbon.
Yeah, that's right. It's like the carbon is acting as a scavenger, pulling out even more gold than was initially leached.
That's pretty cool. Okay, so we've got the gold loaded onto the carbon. Now how do we get it off?
That's where elution comes in. Elution is the process of stripping the gold from the carbon and putting it back into solution.
And how does that work?
Well, there are a few different methods, but the most common one is the Zadra process.
Zadra, that sounds kind of ominous.
It's not as scary as it sounds. The Zadra process uses a solution of sodium hydroxide and sodium cyanide at high temperature to elute the gold.
So you're basically reversing the absorption process.
In a way, yes. You're creating conditions that favor the release of the gold from the carbon.
And the notes mention a couple of other elution methods, high pressure stripping and the AARL process.
Yeah, those are newer methods that can be more efficient than the traditional Zadra process.
So why isn't everyone using those?
Well, they can be more expensive in terms of equipment and operating costs.
Oh, so there's a trade-off there.
There is, and the choice of elution method often depends on the specific characteristics of the carbon and the gold that's loaded onto it.
And once you've eluted the gold, what happens to the carbon?
Well, it needs to be regenerated so that it can be used again.
How do you do that?
Regeneration involves heating the carbon to a high temperature in the absence of air.
And that basically burns off all the impurities.
It does. It removes the adsorbed organic compounds and reactive.
All right, welcome back to the deep dive.